Hello everyone. We are student of VIT University, second year computer science. We are going to give a presentation on context-free grammar under our faculty Professor Kannadasan, and we are giving it in a group of 6 people. Our team consists of Abhinav Sharma, VIshwanath Singh, Anupam Sinha, Anunay Saxena, and VIshesh Gaurav. I am VIshwanath Singh, and I will give the beginning part of this lecture, and I will start with context-free grammar. So, starting with the definition of context-free grammar. Context-free grammar, or CFG, is a grammar which is four-tuple or quadruple system, where V, sigma, Rs are the four-tuple, and where V signifies set of non-terminal symbols. Non-terminal symbols can be all small cases letters, and sigma signifies the terminal symbols. All the uppercases letter comes under the terminal symbols. R signifies the set of rules, which is V to V union sigma star, and S is the starting symbol. So let us start with an example of context-free grammar. V, where we already mentioned, was V already mentioned was a set of terminal symbol. So Q comma F is going to be our V, and sigma, as we signify, was set of terminal symbols. So 0 comma 1 is sigma. R is the set of rules. So R is Q to 11 Q, Q to 00 F, F to 11 F, and F to sigma. And as in the set of rules, we have Q as a starting symbol, so S is equal to Q. And we can simplify the expression using different rules. So finally we get Q to 11 Q, 00 F, F to 11 F, sigma as the set of rules for this particular grammar, and this becomes our grammar. So how do we use these rules? So as if given in the expression, if A to B, then XAY to XBY, and we say that XAY derivates XBY. If S to some expression to T, then we write S to star T. If string X in sigma star is generated by G, if S goes to star X. And so language of G is X in sigma star, where S goes to star X. So we will start with an example. We take G as S, where G is terminal, non-terminal symbol. This is 0, 1, where 0, 1 is terminal symbols. S to 0, S1, and sigma, which is set of rules, and S the starting symbol. So sigma in LG, because S goes to sigma, and sigma is actually null here, null expression, and 0, 1 in LG, because S to 0, S1, and 0, S1 to 0, 1. And next we have 0, 0, 1 in LG, because S to 0, S1. Now we can substitute. As we have seen, S goes to epsilon, we substitute it as 0, S1, and then we substitute S again with 0, S1, so it becomes 0, 0, S11, and finally it becomes 0, 0, 1, 1. So now we can keep substituting the value, and we can say that 0 to the power n, 1 to the power n in LG is because S goes S2 sigma S2 star 0, 0 power n, 1 power n becomes the language for this given grammar. Yeah, so as I already mentioned, LG is a 0 to the power n, 1 to the power n, where n is greater than 0 is the language obtained from this grammar. So now we will move to context-free language. So what is context-free language? Context-free language is a language that is obtained from a context-free grammar, such that L is equal to LG. So if we can obtain a context-free language, as we obtained in the last example from a context-free grammar, we call that language as context-free language. Next, corollary to the given expression, every regular language is a context-free language, and the class of regular languages is a proper subclass of context-free languages. As we can see that the CFL context-free language is a larger set, and regular language is a subset of context-free language. So now we will move to our next section, that is derivation trees or parse trees. So how do we make a derivation tree? Well, that's very easy process. So if we have a given grammar as to AB, A to AA, or lambda or epsilon, B to BB or lambda, and so as to a AB, so we can keep S and as a circle in a circle, and as goes to AB, so we will mark an arrow A, another arrow on the right side B. So this will give the expression as to AB. Next is S goes to AB and A goes to AAA. So we put A, we substitute the value of A as AAA. So we get AAB. So as we see A gives AAA. So A, as we did in the case of S goes to A. So this is the next step for our parse tree or derivation tree. Next we have B. So we substitute the value of B as BB. So we get this expression. And in the tree also B gives to BB, so we get B. And next A goes to lambda also, so we will put branch and add lambda also, and same with the B goes to lambda also. So now we can obtain all the expressions starting from S to A to B to A to BB to lambda. So this will be the derivation tree for the given grammar. And yeah, so the final expressions that we get from this derivation tree will be the will be the leaf nodes of this particular tree, which is A lambda lambda B. So the value we get is A lambda lambda B, where lambda or epsilon are null values, so null strings. So we'll get A B, same value as we get from the manual calculations. Now we will talk about partial derivation tree. So as a partial derivation tree can be considered as an intermediary step to get a complete derivation tree. As in we have S to AB, so S goes to AB. This will be the partial tree of the main tree which we get for this particular expression. And S goes to AB and AAB. So we make tree for this particular expression only. S goes to AB and A goes to AA. This will also be a partial derivation tree of the main tree. So in sentential form, the answer for this particular partial derivation tree will be AA, AB. So in some languages, the leftmost or rightmost derivation order doesn't matter. As we can see in the given example, as we can see in the given example, S goes to AB. We use the leftmost substitution method, which means we substitute the value of leftmost non-terminal symbol first. So we substitute the value of A with AAA, and then we substitute the value of B AAA, then we substitute value of B with BB, and finally we get the expression AAB with the help of left substitution. Now we use rightmost substitution, in which we substitute the value of rightmost non-terminal symbol first, as in we substitute the value of B first, then we substitute the value of A, and we get the same expression. So we are getting both same expression using leftmost and rightmost derivation, and we are getting same derivation tree also using leftmost and rightmost derivation. So in this case the order doesn't matter. So this was all from my side, talking about derivation trees and talking about context-free grammar. Now as we said that order doesn't matter in some cases, but in some cases order does matter, and this gives rise to the condition of ambiguity, which will be
Hello friends, I'll be talking about ambiguity. So moving forward, I'll be just briefing you about what is ambiguity is. So giving an informal definition, like my friend explained about parse tree, that is derivation tree. So we say a language or grammar is said to be ambiguous when it has one or more than one left or right derivation tree or left or right derivation that is on paper. So moving on, we have this language E plus E star E and A. We have a string A plus A star A. So for this particular string, I constructed a leftmost derivation tree with this expression. So this is a parse tree. Uh, the other leftmost derivation for this language is uh, this, with the parse tree looking like this. Now the two derivation trees are, first is this one and the other one is this one for this string A plus A star A. So the grammar is said to be ambiguous when the string A plus A star has two derivation trees, as we constructed the parse trees of the above string A plus A star A. This one is this, other is this. We're using the two left derivations, this one and this one. Now string A plus A star A has two leftmost derivation. That is, first is this, when we replace the first E by A, and then by using the left rule we form this expression and we get the string from out of the grammar, that is A plus A star A. And the other one is this, where we take first E star E as the starting uh, grammar, then we move on with the leftmost rule, replace E by A, and finally we get the same string. So these are the two derivations. Now the defining ambiguity. So a context-free grammar is ambiguous grammar if some string has two or more derivation trees, W belonging to L of G. So the string A plus A star A was there in our example previously. We got two parse trees, two derivation trees. So in with respect to our definition, there are two parse trees. Both are leftmost parse trees. So this grammar is ambiguous. And the other one is with in terms of derivatives. So we derive two derivation. This is left and this is right. So this definition states that a context-free grammar is ambiguous grammar if some string has two or more derivation trees where W belongs to L of G. So here the key word is derivation. Two or more leftmost derivations. The derivation. It can be rightmost also, but we constructed the leftmost derivation, so both can be there because as the definition states that there has to be more than one either leftmost or rightmost derivation. So why do we care about ambiguity? We have the string A plus A star 2. Now let's take A equal to 2 and we had the parse trees we constructed before. First is this and the other is this. So after replacing A as 2, we get the expression the string as 2 plus 2 star 2. So using the first parse tree, we get the answer as 6 and the other parse tree we get the answer as 8. So as we know by a normal calculation the answer would be 6. So the correct result would be like this parse tree, the first one we constructed with that derivation. So it can be concluded that there were two trees, two derivation trees, two parse trees. This first is this, second is this. We got the correct result from this, and the result which was getting 8 was wrong. So this practice in turn is bad for programming languages. So what we have to do is we have to remove ambiguity from the grammar. So for removing that, we'll be constructing a unique parse tree or derivation tree using that language for that same string A plus A star A. This will be like this E plus T. So this signifies that for each string there will be a unique derivation tree or parse tree, which will be something like this: A plus A star A, the expression we had. This is the unique parse tree for this particular string, and the grammar will be like this. And this becomes now non-ambiguous, as it is saying that every string has a unique derivation tree. So for every string or expression, we'll be having a unique parse tree or derivation tree. So moving on, we have inherent ambiguity. Some CFGs have only ambiguous grammar. This means that the example given over here, L equal to A and B and CM union A and B and CM, it can be seen that although this language is a CFG, but it is ambiguous. can't remove the ambiguity from this type of language we are having. As we can see, the string is after union, taking the union, we get the string as a n, b n, c n, which has two derivation trees. As mentioned here, one is this, other one is this. So we can conclude that for this grammar, those are the rules as we discussed earlier. So these can't be, it can't be converted to, the ambiguity can't be removed from these. So moving on, we have simplification of context-free grammars, which my friend over here, Anunay, will take over.
The topic I'm going to cover in this part of the lecture is simplification of context-free grammars. The first thing that we come across the simplification process is the substitution rule. If the uh, question is given to us such as S is equal to AB, A is equal to AAA, A is equal to AB, BC, B is equal to AA, and B tends to B, we will substitute B tends to B. Now the grammar will look like S tends to AB. So since we substitute B with small b, so it will be S tends to A small b. A will tend to AA only. The second A, that is AB, and uppercase BC will convert it to A, to lowercase b and c, and the last b will remain as it is. The substitution rule for the second question in this will be S is equal to AB slash AB, A is equal to AAA, A tends to AB, BC, and AB, BBC, and B tends to AA. We will now substitute B tends to AA. So S will turn out to be AB, AB, AAA, A tends to AAA, A tends to AB, BC, so AB, BC, and AB, AAC. What we have done is that we have removed B entirely from the question. For the second question, like in general, if A tends to XBZ and B tends to Y1, we will substitute B with Y1. So the equivalent grammar will be A tends to XY1Z. Nullable variables. The second procedure for simplification of context-free grammar is the removal of nullable variables. Lambda production. Lambda is a nullable variable. Example grammar: if S tends to AMB, M tends to AMB, and M tends to lambda. M here would be a nullable variable because M is tending to lambda. If S tends to AMB, M tends to AMB, and M tends to lambda, we'll substitute N with M, which is tending to lambda. So the equivalent grammar will be S tends to AMB, S tends to AB because we have removed M because it is tending to lambda. M tends to AMB, so M will also be equate to AB. Unit production. The third process will be the removal of the unit production. If there is a single variable in both the sides, we call that as a unit production. Removal of unit production. If A tends to A, it is removed immediately. Example grammar: if S tends to small A tends to A tends to B tends to A, B tends to BB. In this we can clearly see that there are two very clear unit production which are A tends to B and B tends to A. First we will remove A tends to B. So the equivalent grammar will be S tends to AB, A tends to A, B tends to AB, B tends to B. And now we'll remove B tends to B because as we had studied before, if there is a single variable on both the sides and the variable is same, it is removed immediately. The equivalent grammar after removal of B tends to B and B tends to A will be S tends to AA, AB, AA, A tends to lowercase a and B tends to twice of lowercase b. Now we tend to also remove the repeated productions. Since we can see that small a and uppercase A are repeated twice, we'll remove one of them, and the final grammar which will be obtained after removal of the repeated productions will be S tends to AA, AB, A tends to A, B tends to B. We can see that the final grammar is free from all sorts of nullable or unit productions. Now, my friend will carry on this lecture and explain to you about the removal of the useless productions. Thank you.
Now I am going to tell you about how we will remove the useless production. Here in this question, here S tends to AS, S and S tends to A and C. A is tending to non-terminal A and B is tending to non-terminal AA and C is tending to ACB. First we will find all the variables that can produce strings with only terminals. Here A is producing a small a, that is a terminal, and B is producing AA, which is also a terminal. So these are the two elements which are terminating. A and B. Next, first in round 1 we will select all the non-terminals, and in round 2 we will see the non-terminals A, B and S which are used. Now we will now we will remove all the useless production which are non-terminating. Here we can see C is non-terminating, so we are removing this production. So after that we are left with only 3 production: S tends to AS and S tends to A, and A is tending to A and B is tending to double A. Now in second step, we will find all variables reachable from S. So we can use dependency graph for this. In the dependency graph we can see from S we can reach A, but we are not reaching B. So B is not reachable. So we can eliminate B also because it is non-reachable. So B is a useless symbol here. So after completing this step, we are left with two variables production, which is S tends to AS and A, and A is tending to small a. So for removal of useless symbols, we have done only 3 steps. These steps are: first we remove nullable variables. In second step we have removed unit productions, and in step 3 we have removed useless variables. Now there we coming to normal forms. There are 2 types of normal forms: Chomsky normal form and Greibach normal form. In Chomsky normal form, it is also known as CFG. There are 3 rules. First rule is that for non-terminal A, it should be of form BC, where B and C should be non-terminal, or A should terminate to A small a, which is a terminal, and S, which is production, should be null. Now, the theorem suggests that there is an algorithm to construct a grammar G dash in CNF that is equivalent to a CFG G. So for construction of CNF, we first obtained equivalent grammar that doesn't contain lambda rules, chain rules, and useless variables. We will apply following conversions on rules of the form A tending to B, B small, capital C. And these are the steps which we have followed. A tends to capital B and capital Q, which is of the form we required in CNF, and B and P is the form of small b, which is terminal, Q is BR, R is WC, and W is terminal C. Now coming to the significance of Chomsky normal form. Here we can see this is a parse tree, and for the derivation of this parse tree, the length of string should be of the form 2n minus 1, where n is the length of string. The maximum depth of a parse tree should be equal to n, where n is number of leaps, and maximum depth of a parse tree should be of the form log 2n plus 1, where log 2n is in form of ceiling function and Greibach normal form. We will construct a terminal prefixes that facilitates discovery of dead ends. A CFG is in Greibach form, normal form, if each rule is of the form A tending to small a, capital A1, A2, tending up to AN, and capital A is tends to A small a, and S should be null variable. Theorem. In this theorem, there is an algorithm to construct a grammar G dash in GNF that is equivalent to a CFG G. Now what's the analogy of GNF? We can use it in solving linear simultaneous equations. For example, in here x is equal to y plus 3, and y is equal to 2y plus z plus 1, and z is equal to minus x plus 2z plus 6. So we will find the value of x, y and z by using this equations. So here what we are doing, just back substituting the values of x and y in z, and we are getting the values z is equal to -2, y is equal to 1, and x equal to 4. And example, how to convert to ZNF form. Here in this question, A is tending to capital B and C, and B is tending to CA and terminal B. C is tending to capital AB and terminal A. So first converting A into BC, and B is CA and B. So here we will choose small C and to BCB. So by substituting above A and B in this, we are getting it in GNF form, and we have eliminated left recursion by using the variables A and B. Here we can see C is tend to BCB and AR, BCB and slash A, and R is giving ACB R and ACBB, introducing terminals as first element on RHS. So this is the final product we are getting after substitution, where C tends to BCBR, AR and BCB and A. B tends to BCBRA, ARA, BCBA, AAB, and A tends to BCBRAC, ARAC, and BCBAC, AC, and BC. So at last we are getting R as BCBRAC and up to BC and CBR and CB. So finally, thanks.